So a wing is said to have an aerodynamic twist if the airfoil changes as a function of distance along the span-wise direction. So if the airfoil changes in the span-wise direction, then the wing has aerodynamic twist. For example, let's say that you cut the wing in this part, then maybe that cross section is NACA 2412. If I cut the wing here, maybe this cross section is NACA 4412. So if the cross section is changing in the span-wise direction, then the wing is said to have an aerodynamic twist. And you know that different airfoils have different zero lift angle of attack, right? So if you recall your CL versus alpha, then let's say this is the CL versus alpha plot for an asymmetric airfoil, and this angle, the angle where the lift coefficient is equals to 0, is known as the zero lift angle of attack. And the value of this zero lift angle of attack changes from airfoil to airfoil, right? Just to give you a very, very simple example, if I have a symmetric airfoil, then this zero lift angle of attack will simply be 0, right? So you can imagine that here I have, let's say, NACA 0012. Then in that case, the zero lift angle of attack at this location is going to be 0, but it will be something negative here, right? It will be another negative value here. So in this way, when you change the airfoil in the span-wise direction, you are also changing the value of zero lift angle of attack. In other words, mathematically speaking, you can say that a wing has aerodynamic twist if the zero lift angle of attack is a function of location in the span-wise direction. Okay, so just to write it mathematically, we can say that geometric twist means the angle of attack is a function of y, and aerodynamic twist means the zero lift angle of attack is a function of y. Another thing is that if there is a lift distribution, so if the value of lift changes as a function of distance in the span-wise direction, that means the circulation is also going to change, right? Because from the Kota-Jakowski's theorem, we know that the lift per unit span is equals to density times the velocity times the circulation. So if there is a lift distribution, so if lift is a function of y, then obviously the circulation is also going to be a function of y. And this becomes an important thing to be kept in mind, because when we develop the theory, in the theory, if you may recall, based on our discussion of the flow over an infinite wing, in the theory we are basically trying to find the correct value of this circulation or the vortex strength, right, which would give us the correct value of the lift distribution or the correct pattern of streamlines around an airfoil, right? So that's why, although physically speaking it is enough to understand that the lift changes in the span-wise direction, but theoretically speaking it is also important to connect this with the circulation being a function of y. Okay, so I'm going to very briefly give you an idea of how the flow over a finite wing is modeled. Okay, this is similar to how the flow over an infinite wing is modeled. This is what we discussed in the flow over an airfoil or flow over an infinite wing. But here I will show you just very briefly, just give you an idea how the flow over a finite wing is modeled. Now, in this case, for the flow over a finite wing, you will basically put a bound vortex, okay, along the span-wise direction of the wing. So let's say this edge is at negative b over 2 and this edge is at b over 2. So what is a bound vortex? Bound vortex just means it is not extending to infinity. Okay, so this line, it is basically a vortex filament. So every point here on this line is a point vortex. Okay, but this vortex filament only extends from negative b over 2 to b over 2. So in addition to that, there is also a semi-infinite trailing vortex filament at the boundaries, like so at negative b over 2 and b over 2. So there are also these line vortices or vortex filaments. So this one has a source vortex at each point, and they will also induce flow in the circular direction. Okay, but this one piece is not enough. You have to add other pieces as well. So let's give a name to this piece. This is called a horseshoe vortex. Horseshoe vortex. And this segment, which extends from negative b over 2 to b over 2, or any such segment which is basically a line of fixed length containing a vortex source at each point. This is known as the bound vortex. Okay, so when I say horseshoe vortex, I mean this and this all together. When I say bound vortex, I mean only this line. Okay, to properly model the flow over a finite wing, you have to add the stream function and potential function, right, created by this horseshoe vortex with other horseshoe vortices, which will be added as I'm going to show now. So for example, you will put another horseshoe vortex like this, and you will put another one like this. So there could be many such horseshoe vortices which will be superimposed, and they all share a common line here. Okay, so this line is known as the lift line. And so if you consider this part here, you are combining the contribution from all the horseshoe vortices that we have put here, right? Because this part of the lift line is common to this horseshoe vortex, this one, as well as this one. Okay, similarly, this segment of the lift line is common to two horseshoe vortices in this example, this one and this one. Okay, so in this way, when you will add their strengths, you will see a distribution. Okay, so since we are superimposing three horseshoe vortices in this segment, the combined let's say the combined vortex strength arising from this section will be higher than in comparison to the vortex strength in the side, and then when you go further away, it will be even lower. So in this way, you will be able to get a profile for the vortex strength as a function of y. Okay, y means in the spanwise direction. And from this profile of vortex strength or circulation, the same thing, you can obtain the lift distribution. Okay, so the math has a lot of details, and we don't have time to go through those details. So I'm only going to now focus on the results, and based on those results, we can also do some numerical problems. So one of the results from this type of analysis is that the induced drag coefficient is equal to CL square divided by pi AR 1 plus delta, where this delta is called the induced drag factor. Okay, so this delta is induced drag factor. Now you may have seen this before as well in the fundamentals of light, right? So when you saw this in fundamentals of light, it appeared to you as CDI equals to CL square divided by pi EAR, where this E was called the span efficiency factor. So you can easily see how now this span efficiency factor is related to the induced drag factor. Okay, so the span efficiency factor is equals to 1 plus inverse of 1 plus delta. Okay, now the value of this span efficiency factor or induced drag factor, it will depend on the shape of the wing. It will also depend on the aspect ratio of the wing. So this actually gives us a good context to also talk about the tapering feature of the wing, right? So you may have obviously noticed that the wings are usually tapered. At the root, the chord is shorter. Sorry, this is the tip. At the tip, the chord is shorter than at the root. So let's say that the chord at the tip is represented by CT, and the chord at the root is CR. Then this ratio CT over CR is called the taper ratio. Okay, so this is called the taper ratio. So this induced drag factor or the span efficiency factor, this is a function of the taper ratio and the aspect ratio of the wing. Okay, and you will see that very clearly in figure 5.20 of the book. Okay, it shows how the induced drag factor changes as a function of the taper ratio and the aspect ratio. So if you look at this figure, basically it looks something like this. So let's say this is your induced drag factor and this is your taper ratio, CT over CR. So, and this lower curve is a smaller value of aspect ratio. Okay, so we don't have an equation for this. So far as we are concerned here, we will just have to read the value for delta from the plot for a given value of taper ratio when we have to calculate the induced drag coefficient. Okay. Now, so again, I have not directly addressed why the wing needs to be tapered. Now you can see that depending on the taper ratio, you will get a certain value of delta that controls the value of the induced drag coefficient, right? So if this delta is a big number, then you are basically increasing your drag. And if this delta is a small number, then the drag is also small. So the question is what is the best possible shape to minimize the induced drag coefficient, right? So this delta is going to be greater than 0. Okay, the lowest it can be is equal to 0. Okay, so this delta is equals to 0 when the wing is elliptic in shape. Okay, so you have to note that for elliptic wing, delta equals to 0, and this gives you the lowest value of induced drag coefficient. Now what does this delta equal to 0 correspond to? The span efficiency factor. When delta equals to 0 here, the span efficiency factor is equals to 1, right? So E equals to 1. Okay, so this will give you an elliptic wing. Elliptic wing is basically shaped something slightly curved shape. Okay, and this is a really bad drawing, but you can imagine that it is curved. It's not simple like a rectangular wing, right? For a rectangular wing, actually the value of this delta is quite high. Okay, so the best we can do is design an elliptic wing in order to reduce the value of CDI. But the problem is because this shape is so sophisticated, I mean there is a very well defined curvature, it is difficult to manufacture and it could also be expensive to manufacture. Okay, so the cost of achieving a very low value of CDI based on controlling this delta is quite high. But on the other hand, if you have a rectangular wing, then it's easy to manufacture, but the trade-off is that you will now end up with a high value of induced drag coefficient. So the compromise between the two is this tapered wing. Okay, so here it is relatively easy to manufacture also, and the value of CDI will also be quite less. Okay, because the delta will not be as high as it would be in the case of a rectangular wing. So this is one of the advantages of having the tapered wing. This is also the reason why all the wings are tapered wings. Now, in terms of the value of CDI, it is more sensitive to the value of AR. The reason is, practically speaking, this delta only changes by about 10%. Okay, so if you go back to this figure and if you look at this figure, you will notice that the value of deltas which are plotted, okay, they will only change for in a practical scenario, they will only change by about 10%. But the value of this aspect ratio can change from anywhere between 6 to 22. Okay, so this is a bigger change than just a 10% change in delta, right? So when people want to reduce the value of induced drag coefficient, then they will try to achieve it mostly by increasing the aspect ratio. Okay, so this is the reason why one might prefer to have a wing which has a very long span. Okay, so in this way, the aspect ratio is also important for the drag characteristics.